You're back, and it's Independence Day. Oh, just kidding. All right, not Independence Day, but we are going to talk about linear independence. And I thought I was being cute. Wasn't that cute? Yeah, that's fair. All right, some definitions: independent versus dependent. Right. So the idea of independence versus dependence. Again, if we think back to independent versus dependent variables, it's going to be kind of similar to that idea, where if it's independent, it makes its own decisions, it's on its own. If it's dependent, it relies on something else to be true or to exist, to do something. I don't know, whatever you want to call it. In this case, when we're talking about our linear equations or our vectors, we want to talk about whether or not vectors are linearly independent of each other or whether they are linearly dependent of each other. By definition, what that sort of means is for vectors to be linearly independent, what we mean here is that they are not linear combinations of each other. And the way that we're going to show this is we're going to set up a vector equation, and we're going to set up a homogeneous vector equation. And as long as the trivial solution is the only solution, then we can say that they are linearly independent. Because if the trivial solution is the only solution, that means the only thing I could multiply each vector by is 0 in order to get the 0 vector. And that means that they're not combinations of each other. On the flip side, if they are linearly dependent, this means that they are linear combinations of each other. And what that means is that we could write a single vector that is a combination of all of the other vectors times some weight, right? If you think about our definition of linear combinations, this was our definition of linear combinations. Now it was equaled C something, or I don't remember, where did it go? Our definition of linear combinations. Well, that guy disappeared. Hold please. Yes, is that this is some vector. Oh, hey, look, it's the 0 vector. Okay, but yeah, that's basically our linear combinations there, is that definition. And essentially what that means is that they are all within the span of each other. We'll talk about that in a minute. But all we want to do, so back it up, slow it down. All right. To test if they are linear combinations of each other, we're going to write this equation, do our row reductions, see what our solution looks like, and make a conclusion from there. And that's all she wrote. So we want to determine if V1, V2, and V3 are linearly independent or dependent. So in other words, we want to know, is there something that I can multiply each vector by in order to be combinations of each other, right? So is V2 some combination of V1? Is V3 some combination of V1 or V2? So we want to see if these are linear combinations. So the first thing we're going to do, so to determine if this set is linearly independent or dependent, is we're going to assume that it's linearly independent, and we're going to set up that equation. So I'm going to set up that x1 times 1, 2, 3, so times my v1 vector plus x2 times my 4, 5, 6 plus x3 times our 2, 1, 0 vector, and we're going to assume that it's equal to the 0 vector and see what happens. Now, in this form, in vector equation form, not very helpful. So we're going to turn this into the augmented matrix form because we know how to handle augmented matrices. 4, 5, 6, 2, 1, 0, 0, 0, 0. All right, so we're going to do our row reductions, and we're going to see what conclusions we can draw from this. So another symbol that I'm going to introduce here, and you'll see me use it a couple of times today, is this little tilde. Now we use this symbol to represent row equivalency. So what that means is that between two vectors, if all I've done to them is some elementary row operation, so one of those three operations where I can either switch them, I can multiply one, or I can add one and add a row and a combination of another row. If all I've done is an elementary row operation, then the next vector or the next matrix, stupid, me, not you. The next matrix is row equivalent to the previous one, which means we haven't changed the system, we've just changed what it looks like. That's all that means. So this one, if I think about doing my elementary row operation, so I'm going to do two operations at once. I'm going to use the top, I'm going to use row 1 to eliminate the 2 and the 3 in that first column. So I'm going to take this row and I'm going to take row 2 minus 2 row 1, and then here I'm going to take row 3 minus 3 row 1, and I'm going to end up with the vector equation, not vector, matrix, 1, 4, 2, 0, 0, 0, 0, 0, negative 3, negative 3, negative 6, negative 6. Oh, hey, that's fun. Now, those are equivalent, aren't they? They are exactly the same. In other words, I can divide this one by negative 3, I can divide this one by negative 6, and I get the equivalent matrix 1, 4, 2, 0, 0, 1, 1, 0, 0, 1, 1, 0, and it turns out that if I add these two things together, so if I replace this with row 3 minus row 2, then I get 1, 4, 2, hey, 0, 0, 1, 1, 0, 0, 0, 0, 0. And I honestly don't have to go any further because I am at the point where I can make a conclusion. In other words, if I take a look at my leading entries, there's no leading entry here. I got rid of that row. It's all zeros. Because of that, I have 2 pivot points, but I have 3 variables. That means I have a free variable, which means that I have an infinite number of solutions, which then means that these are not independent. So these are linearly dependent because I have a single free variable. So that's another way to think about it. What we're looking for is if I can get down to the solution, or if I can get down to all ones in the diagonal, and I still have all zeros, then that tells me that my solution is, or that my system is linearly independent. So, in other words, okay. So, since we are not independent, we can find a single linear dependence relationship among V1, V2, and V3. So in other words, I want to go look at this idea, and I want to figure out, or I want to write an equation using, so I'm going to find some weights, some C1, C2, and C3, so that I can write those equations. So essentially, all I'm going to do is I'm going to substitute for my free variable, right? So x3 is my free variable here. And if I think about writing these, so this one says x1 plus 4x2 plus x3 is 0. And then the one at the bottom says x2 plus x3 is 0. So x3 is my free variable, which means that I can pick a value for it. And then I can also, you ready? Since x2 equals x3, why is that not making sense? It is. Okay, cool. If I pick a variable, so I'm going to pick a value for x3. So I'm going to let x3 equal, we'll be nice and easy, 1. that tells me that this relationship tells me that x2 is -1. And then if I plug both of those in there into the first one, x1 plus 4 times -1 plus 1 equals 0, tells me that x1 equals 3, right? 4 plus 1, oh, -3? -3. Yeah? Yeah. No. Hold, please. Ah, figured out my mistake. Anyone at home screaming, going, wait, 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 wait! You wrote the wrong equation! Hope you were. That should be a 2. Yeah, it should. So then we have, this is, so -4 plus 2, x1 plus da-da-da-da, so x1, let's try that again, x1 is 2. Okay, that makes more sense. So our linear independent, or our linear dependence relationship based on these x values. So now this is just one among an infinite number. So our equations, we go up here, so our C1 is whatever we found for x1. So that's 2 times our v1 vector, which is 1, 2, 3, yay, minus, and it's minus because x2 is -1, so minus our v2 vector, which is 4, 5, 6, plus and our v3 vector 2, 1, 0, and this should be a true statement, so this should equal 0, 0, 0. Another way to write this is because we've already defined v1, v2, and v3 upstairs, up here, we've defined them already, so we could write this as 2v1 minus v2 plus v3 equals the 0 vector. Ooh, don't forget your little vector hat. All right. When we come back, we're going to talk a little bit more about linear independence of matrix columns. So talking about the linear combinations, or talking about what happens when we look at each column of a matrix as its own vector. Come on back now, you hear?